just take up all the camera. Cheap way to do it. So, okay, well, I'll just hold this up and that'll capture both of us. That'll get me and you,
okay,
more or less.
Sure.
Okay, so yeah, this is Luther Kruger here, Big Blue Sun Museum of Solar Cooking based in Minneapolis. And I'm here with Alexis Zeigler in the Low Energy Farm?
Living Energy
Farm.
Farm.
Living Energy Farm. Living, that's better than Low Energy Farm. For some reason I first read it as Low Energy Farm, and I thought, oh, is this a place where everyone's just sitting around in hammocks, you know, real dragging their feet, low energy?
No, we work pretty hard for better workers.
Oh yeah, no, it's the way to go. So anyway, Alexis has agreed to just give me a quick tour of the stuff he's doing, starting with the solar cooker. It's a DC direct to a heating element
yes.
Cooker, so it's a solar PV to electric cooker, much along the lines of Pete Schwartz, who I had a really nice episode with, and so some of this might be familiar, but I'm thinking there's probably going to be a twist or two. And then just a quick tour of the shop after this. So
sure.
So yeah, so tell me about this cooker.
So at Living Energy Farm, we have 10 to 12 people living here year round, and we don't bring any propane in. It's all we're 100% energy self-sufficient on the farm at a residential level. We still have some gasoline, diesel going into the tractors because we earn our living and grow our food, and we're working on getting rid of that with a few different technologies. But in terms of cooking, there's, I think, a real disconnect between the mystique or the idea of solar cooking and the reality. I've had friends of mine spend gobs of money and decades of time traveling around the world trying to help low-income people set up solar cookers. They set up the cookers, and these are not small projects, and they are not widespread and not widely used. I think there's a real misunderstanding that poorer people or people of color have a lot of time on their hands and they can sit around and wait, or whatever. It's like, no, they live a life kind of similar to ours. They have a job, they need to work, they need the cooker to work, they need to cook their food. So what happened at Living Energy Farm when we set out, we're 13 years old, this is 2024, we set up, of course, the sun oven style cookers. Those cookers are super easy to make. You can make them homemade or buy them. And they work okay, but they only really work in good weather, nice sunny weather. It needs to be pretty warm. If it's bitter cold outside, they're not going to work. If it's cloudy, they're partly cloudy, they're not going to work. So they're okay. And then we have a parabolic cooker, the satellite dish style cooker. And that one was it's actually a repurposed water heater system.
Oh, sure.
But in any case, and that was a little easier to use. You could get a little more heat out of it, particularly in less than optimal weather. But for a number of years, we cooked certainly, in the wintertime, basically not at all. And in the summer, we cooked some on the solar cookers. And we don't stand on top of the cooks and demand that they do, we have different people cooking. This is an ongoing project. We have interns coming through, and we eat 3 meals a day right here. We grow our own food.
Yeah.
We don't buy any flour. We're grinding our own flour, direct drive with DC motors. We take that flour, we cook with it. We grow our own beans. We grow our own sweet potatoes and corn. And so we're doing it for real here. This is not pretend. And the direct thermal cookers seem like a great idea, but on an annual basis in Virginia, we were doing somewhere between maybe 5%, 6%, a little more in the summer of our annual cooking was happening on solar cookers. Just not a lot. So, and I have always been resistant to make solar electricity into heat. Certainly the idea that we're going to take industrial society and heat people's leaky homes with industrial solar fields that then get stored in industrial lithium battery plants, and you're going to heat these houses. It's crazy. It's off the map crazy. It's not even remotely possible.
And with each step that you add, it reduces the energy you've got, right? I mean, you lose,
There's attrition,
Exactly.
Major attrition. What we have is the opposite. We call it leveraging.
Yeah.
So that you can hear in the background now the blower running here in the kitchen. That's a DC blower running direct drive, but it's pulling, for every watt going into that motor, we're pulling 100 watts of heat off the roof. Hot air collectors, which are cheap to build. The air is blowing under our feet as we stand here, so we'll drive that heat into the floor, and then the building's reasonably warm the next day. The main house is separate from the kitchen. The main house stays a lot warmer than the kitchen. That's just design. But in any case, So with the solar cookers, I played around in my head with various designs to try to improve our situation, but I was reluctant to make electricity and heat. Just instinctively, you don't do that. But at some point, I ran into Pete, and he was the inspiration, definitely. Pete Schwartz, Cal Poly, and he was making very small, very inexpensive cookers, just direct drive to a homemade heating element. He had various iterations of how he did that, and the light bulb was like, dang, of course. Because a simple nichrome wire, nichrome is nickel chromium, that's what you got, the little glowing wires in a toaster, that's nickel chromium. Probably 95% of the electric heating elements on the planet are nichrome. It's super cheap, almost free. So you can make a heating element. One tricky thing about DC, with AC, there's resistance. It's like opening a valve. And with AC, the more you open the valve, the more electricity comes through up to the limit of your circuit breaker or whatever. With a photovoltaic, particularly direct drive system, it's a bell curve. And at the peak of that curve, there's an optimal power usage level, an optimal resistance level. So you don't want to overshoot your resistance. You won't get more. You're not going to get more than 100 watts out of a 100-watt panel, and you rarely actually get 100. So there's a little bit of difference in the calculation, but you can make homemade burners, or you can, if your power level is right, you can buy burners. We buy burners out of China now. We're sending cookers to, our biggest project is in Puerto Rico, and we promote these cookers in the US. So when we went to insulated solar electric cookers, and our cookers are a little bigger, more powerful, more expensive than what Pete is doing in California, our rate of amount of cooking that we did for 10 people year-round in Virginia went from about 5% to 80%. Huge difference. So this cooker in particular does probably 70% of our cooking right here. And this is not a small unit. This is connected to our direct drive 1400 watt 180 volt solar rack. Now that's just 6 solar panels, but that 6 solar panels, it's 1.4 kilowatts, 1400 watts, is connected to about 16 kilowatts worth of demands. Now we don't run 16 kilowatts all at once, but we, on a sunny day, will easily run 3 or 4 kilowatts. And it works. So we can cook for 10 people in this cooker while I'm out cutting metal in the machine shop, the heating blowers are heating the house, all for 1400 watts. It's an amazingly efficient system, particularly compared to the battery-based systems. So what this is, we started out, this is just duct metal, 26 gauge galvanized, pretty cheap. We started building them that way, but you can see this, like it starts to rust out on the inside. So this one is actually stainless steel. We do a stainless steel inside. The smaller cookers like this one, that's a homemade nichrome burner in there. Again, the resistance is set to the power supply. These are stovetop burners. Because this is a high voltage unit, and the way we do it, we can do single burner, parallel series. Again, we're trying to hit that maximum power point, or as close to it as we can get. So you just pack this thing full of, for whatever you want for lunch, you pack the food in here in the morning, and then it's done at lunchtime. You pack it after lunch, and it's done by dinner. So this easily does most of our cooking. And the crazy thing about this, now Virginia, we're kind of in the middle in that we have moderately cold winters and moderately hot summers. Certainly in the summer, everything solar is easier, but in the wintertime, we can have partly cloudy, bitter cold outside. It can be, we don't often go below 0, but it could be 10 degrees outside, Fahrenheit, and partly cloudy, and I still cook on this thing. That's what's the huge difference between all of these solar thermal cookers, the idea of how they should work and how they really work. This cooker is indoors. You're not expecting an overstressed, worried cook to be running in and outside to the cooker. They're right here chopping vegetables, putting stuff in, taking care of it, watching it. And it cooks in bad weather. Now that's also a big difference. I really respect what Pete's doing, and his cookers are much cheaper. For so low-income people, you can't, somebody in sub-Saharan Africa would really struggle to do this. This would be more of a village-level cooker. But that said, a 12-volt cooker, 24-volt cooker, not going to work in cloudy weather. Just not going to happen. My 180-volt cooker, we can have overcast, not like heavy overcast, but light overcast, bitter cold, and I'm still cooking.
Yeah, I'm surprised that we have 6 kilowatts on our roof and net metering, and I'll look outside and I can kind of tell where the sun is, and it'll be 800 or 1,000 watts.
Yeah.
It's now that's 6 kilowatts of panels though too.
Yeah,
So.
yeah. I mean, you definitely take a loss.
Yeah, yeah.
But this has got 2 inches of rock wool all the way around it. And the interesting thing about this, and we have a little analog voltmeter here, and this goes back to the P-max thing, the power max point. On a sunny day, I'll kick it down on one burner, and you see we popped up, we're about 120 volts. That's pretty good. But as it starts to get more overcast or later in the day, I'll actually kick 2 burners in series, and see we popped up to about 140 volts. What that means is when the system's heavily loaded, I'm actually getting more power with more resistance. That's the opposite of AC. And you're going to cook more slowly. You're not going, this is not a frying pan. Although we do, I can show you over there if you want to see it. You can take an ordinary hot plate and just run it DC. Now that's not super efficient, but it does work. The only difference, or one difference, you know, with this, with the 2 inches of rock wool around it, you can really build up heat. With your hot plate, you know, you're sucking down quite a bit of power, and that's, you know, you're losing your energy pretty quickly. So this, you know, you can build up heat, so on a partly cloudy day it'll cook better. The other accommodation you've got to make, particularly for high voltage, at 12 volts, 24 volts, you don't get a lot of arcing on the switches. We mostly run 90 and 180 volt systems. And the reason for that is that we do so many other things. So we run shop motors, you know, lathe, mill, bandsaw. We run seed blowing, cleaning, seed drying equipment. You know, our flour grinder. All of this stuff runs DC motors, and 90 and 180 volt DC motors, industrial motors, are easily available. And this is another big kicker. Any motor that you can pick up and walk around your house with, like a blender or food processor, vacuum cleaner, even an old-fashioned power tool with a cord, that's a universal motor. 90% of those motors run straight DC. So if we do 6 panels in series, you can do 3 and 3, 3 in series and parallel, 3 in series, and you're in the 90 to 120 volt range, and then you just plug in your blender and run it. The trick is that the DC arcs pretty hard on the switches. So you cannot take an AC switch and run it at 10, 15 amps, 90 or 180 volt DC. That switch, the blue arc is pretty hot, it'll destroy your switch. There's 2 ways around that. One is we use disconnect switches, knife switches, and they are pretty heavy duty. The other thing is what are called snubbers. There's a number of different kinds of snubbers. They use them a lot in electronics. The simplest version of a snubber, what we use, works pretty well. It's just a 50-cent capacitor. It shorts the switch, basically, which, again, is a little counterintuitive, and it, for the most part, makes that arc go away. And we started doing that about 1.5 years ago, so it's kind of an ongoing, making sure this works okay. But so far, we've been able to, even with something like a thermostatic switch, like a thermostat on a hot plate or something like that, or tools out in the shops. I've got hand tools out in the shop, Ralph. The snubber is up inside the tool, so you don't even know the difference. It seems to work fine. Now, as the voltage and amperage goes up, that arc gets harder. So if you ever get a dead short and you've got a lazy switch and you don't have a snubber on it, it's gone. And even with the snubber, you know, it's not 100%, but so far we have been doing fine with snubbers on heavier switches or even on light switches. So this is a fairly inexpensive drum switch, eBay, like $15, and we have snubbers in it. And it's a, you know, drum switches, different drum switches have different configurations, but this lets us do the series parallel arrangement. It's got a lot of contacts in there that are set up in such a way that you can do different switching arrangements for different burners. So the slightly smaller cookers like this one, this is also stainless steel inside. And again, depending on how we're setting it up, we might use a stovetop burner, we might use a homemade nickel chromium burner. This is what we've been distributing in Puerto Rico. We can make them for a few $100, not free, but not crazy expensive. So we can set up a household with a cooker, you know, water pump, refrigerator, do the whole thing, DC, all direct drive. And then you have a really small battery set just to run the lights and to run some electronics. Modern electronics are fairly efficient. They don't need a lot of power. So that's the basic idea. And, you know, for us, this is not an experiment where we, you know, live one way and tell other people to live a different way. We live this way. So another, you know, technology we have is biogas. And of course, there's a lot of biogas in the tropics. It's much easier in the tropics. You know, for biogas, you've got to have some sort of big containment. Of course, plastic is the easy way to do it. Historically, it's been done other ways. And, you know, the two things is you need to feed it and you need to keep it warm. And in the tropics, the keeping it warm part is a whole lot easier. It's a real investment in hardware. We have thousands of dollars in the biogas system now, but it works. So at this point, we've had a lot of issues. We've been working on biogas for years, and doing a large biogas system in a temperate climate is a challenge. And then we've run into other stupid problems. The rats got into it last year and messed some things up.
It's food after all.
Well,
at one stage.
Well, in shelter, it's what we have. We have a 7-foot diameter, 7-foot tall tank. That's 200,000 nominal gallons, although there's a gas bubble at the top. So the digester area is about 1,500 gallons. 3 feet of straw all the way around it. So 2 straw bales all the way around it. Solar thermal heating coil. And you know, the solar electric cookers are great. The solar thermal, we do a huge amount of solar thermal here. Solar thermal is good for moderate temperatures. Like keeping a building warm, you need 65, 70 degrees in the winter. That's easy. The problem with cooking is you can't cook at 70 degrees. You know, to take a shower, you need 105 maybe degrees in the wintertime. You can't cook at 105. You need several hundred degrees to cook, and that's where the electricity comes in. Even fairly low power electricity can achieve really high temperatures given the right setup. So that's the advantage of the solar cookers. Insulated, of course, makes them more efficient. The biogas and the solar cookers complement each other pretty well because the biogas is not time sensitive. You know, Pete at Cal Poly, he's tried to do thermal storage, and that's fine. But thermal storage with electricity, it's more complicated, so we don't do thermal storage on the electrical side, although we might go back in that direction. We've been thinking about it. With the biogas, we can store it. We've got bladder tanks, we store it. So a normal rhythm here on a moderately sunny day is breakfast on the biogas and lunch and dinner in the cookers, and then I still have enough biogas. My kids always want a snack before they go to bed, so the biogas covers the late night snack as well, and that covers us. Now, a cloudy day, if we have a string of cloudy days at this point, we're back on the rocket stoves with the wood, which I really have learned to despise rocket stoves. But
well, elaborate on that briefly.
Well, just we've been here for 13 years, and getting up on a cold winter morning and a smoky ass little fire, and you got to get going. I'm just over it, you know. I mean, it's not cute anymore.
Yeah.
I mean, it works, and it's cheap,
yeah.
but
are they as efficient as burning wood versus the 3-stone fire as you
I
hear?
mean, rocket stoves are better, but they also require a lot more tending.
Yeah.
You really got to stay on top of it.
So they're kind of like
So-
the parabolic of a wood stove. With the parabolic, you got to keep shifting them.
Yeah, it's true.
Yeah.
So I don't, you know, rocket stoves are fine, and you know, there's a number of organizations that distribute rocket stoves and more efficient cookers all over the world, and that's fine for what it is,
Yeah.
because wood is, of course, always a low-end fuel, you know. But it's, you know, the same reason people in New York City don't want to cook on wood is the same reason people everywhere else in the poorer countries don't want to cook on wood. It's smoky, it's a fire hazard. I mean, it's fine for what it is. You know, it's better than nothing, but biogas and insulated solar electric cookers are way better. And on a planet with 8 billion people, and of course, you know, what you're going to do in sub-Saharan Africa is different than what you're going to do in Sweden or Finland, I don't know. Up there, maybe, you know, wood, they have forest, I don't know. Different challenges in different regions. But for us, we've been working on the biogas. We did biogas, you know, like 12 years ago, just a small project. And then we actually tried to do high temperature solar thermal storage, no electricity involved except to run pumps. We put about 7 years into that. Finally gave up on it. It's too expensive, too complicated. They do it on an industrial scale, of course, molten salts and all of that. That is not simple and cheap to do.
No, that's not a DIY. I mean, when I think
Yeah.
DIY, that's several steps beyond.
Right. Well, and there's other concerns too. If I go back to thermal storage, so Pete at Cal Poly, and again, what he's doing is great. They're doing thermal storage with aluminum discs. He had used, you know, sugars in the past, and that's interesting. And I'll be curious to see where that goes. You know, he's focused on the cookers. We have a lot of projects here. But in any case, the thermal storage is a double-edged sword because let's say you get up, it's 8 o'clock in the morning and you want to cook lunch and your thermal storage is cold. you're dumping heat into your thermal storage. And I'll tell you, the single most difficult aspect of solar cooking across the board is predictability. With the biogas, we have this manometer, just a gas gauge on a biogas, so I know I need 2.5 inches to cook breakfast. I just finished cooking breakfast and we're down slightly below 2 inches. So I could not cook breakfast again. But I can look at that, I walk in, I know how much gas I got, hands down. The heartbreak with these solar cookers is, I don't know what the rest of the world is like, but particularly in the winter, in this area, the cloudiness can be really unpredictable. The weather forecasters are pretty good at predicting temperature. They say 55 degrees, we're going to be in the mid-50s, you know that. But we have had more days than I can remember where they say full sun and we get full clouds. Or they say a little bit of sun and we get a whole lot of clouds. So it happens quite often that somebody fills the cooker and then it just clouds over. And then your food either doesn't cook all the way or cooks half the way, and even, the new people. So cooking in general is a skill, of course. A good cook is a good cook and pretty different than a not so good cook. And, I espouse a plant-based diet. I think that's 8 billion people can't eat like Americans do. But it does require more skill. If you're starting with cornmeal and sweet potatoes and some greens and some spices, that's a lot more skill than buying a frozen pizza. And so these cookers, with their unpredictability, for better or worse, it is a challenge to cook it. It is a skill, and it takes, some people pick it up quickly, some people never really get it. And part of the skill is looking out the window, looking at the weather forecast, thinking about, okay, what am I going to get out of these cookers today? And planning ahead. That's the real difference, any kind of solar cooking. It's not more work, but the timing of when the work happens is a big deal. So you're not going to come in here at 11 o'clock and put out lunch by 11:30. Not going to happen. You're going to pack these cookers at 8, 9 a.m. and by 12 you're done. Although you can burn things too. We've done plenty of that. So yeah, it's more skill. It is more challenging in terms of planning ahead. But once you learn the skill, we can do all of our cooking on biogas and electric most days. And at this point, the biogas has been a struggle for some random reasons, like rats and whatever. But we're getting closer. And at this point, what we really need is just a little bit better to streamline our feedstock a little better and then get a little more storage. We'll be done with the firewood at that point. So when I give tours of LEF, one thing I tell people, Living Energy Farm, is that, if you're looking for a magic bullet technology that makes renewable energy work, solar, wind, all these, it's cooperation. You cannot do good solar energy systems for one person or a couple. You just can't. And now, electric systems, okay, you can scale those up and down. We've all got rechargeable batteries these days, but, there's a difference between powering that and powering our life. These things are efficient, fine, and they're not sustainable either. Lots of rare earth metals in that. Our grandchildren are not going to be using these. So in terms of what are our grandkids going to do, they're going to live in cooperatives. They're going to have to. Now, it's a question of whether we do that by choice or we're forced to do it. If you look at solar thermal systems, so outside, it's a lot easier in the tropics, but as soon as you get outside of the tropics, you don't want to freeze to death and you don't want to take a cold shower in January. There's no way. It's funny because you look at a solar thermal panel, 3 times as efficient as a solar electric panel per square foot. But money. Okay, the reason we have shingle roofs instead of sheet metal roofs is because the shingles are a lower skill job, so the roofing contractors can hire low skill workers. They get it streamlined, they make a profit, so they promote shingles. So we have shingle roofs, even though they're an environmental abomination. Enamel metal lasts basically forever, for a long, long time. Same thing happens with photovoltaic, solar electric, versus solar thermal. Solar thermal is 3 times as efficient per square footage, and when you add it, you combine that with good insulation and cooperative usage, you've got a great system. But the profit is in the solar electric. It's subsidized and it's fast and it's lower skill. You don't have to know how to solder pipe. You don't have to know how to build good buildings. They're popping all these solar panels all over the place. That's not an environmental solution, not for 8 billion people. So, what tends to happen is people want to think in simple terms. Is it good? Is it bad? And I know what's happening on, you might call it the left, or part of the environmental movement now is saying solar is bad, because there's so much going on now with the massive expansion of mineral mining, lithium mining, and displacement of indigenous peoples and bulldozing forests, and that's all bad. But there's a difference between living on, 200 watts versus 2,000 or 20,000. And you know, if we go through some sort of god-awful collapse, and I'm not wishing for that, if we're going to avoid the collapse, or we're going to have something after the collapse that is better than, you know, whatever horrible scenario you want to predict, it's going to be at kind of an intermediate level of industrialism. We need to be able to make bicycles. We need to be able to make durable plastic water pipe. We need to be able to make rubber bicycle tires and solar electric cookers. And we can live on maybe 100, 200 watts. And in the tropics, you can live on 50 or 100 watts per person. Colder climates, 100, 200 watts per person, and covers all your energy demands. If it's cooperative, you got a thermal shell around the big building. You've got, once you've got good insulation, I like straw bale, but there's other ways to do it. And then you leverage direct drive systems, running blowers, pull the heat, push it under the floor. The whole system can be tremendously efficient. And in terms of technical difficulty, compared to sending people to the moon, or building airports, building interstate highways, this is stupid simple. It's really easy, it's really simple, but it is a lot like food, you know? So we've been promoting the direct drive system. We discovered it, you know, some years ago and realized, wow, this is great. You know, with an AC system, if you've got a shop with 5 horsepower worth of motors, you've got to have 8 horsepower worth of inverter and supply and batteries. It's crazy expensive. I've got 10 horsepower in my shop. Well, not 10. We've got 16 on the whole farm. I probably have 7 or 8 horsepower in the shop. So lathe, mill, bandsaw, drill press, 4 grinders, compressor, the whole deal. 1.4 kilowatt supply. And what'll happen if I'm out there, I was out there yesterday milling steel, the blowers are on, the system is already loaded down, I turn on one more motor, things just slow down a little bit. Nothing breaks, nothing blows up. Now on a cloudy day, it's like, okay, my mill's not running, I'll go turn off something else for a few minutes to cut my steel. So there's a little bit of management. But it is a much simpler, a much cheaper system. And the solar cookers are a critical part of it. I know a lot of people have a lot of opinions, but these work. These really work. I don't want something that's an idea that doesn't work. They're moderately priced. People can use them. Lots of people can use these. And you know, if we want to adapt them more, we could put timers in them so you could go off to work, put your cooking food in there, have the thing turn on at a certain time of day, put thermostats on them. There is, I don't see it right now actually, but there's a Chinese company now. So the direct drive idea certainly has spread. So water pumps, for instance, because there are so many farmers, whatever they're growing, all over the world that want to do water wells far from the grid, there's a huge supply of water pumps. You can spend $20, $20, $2,000, $20,000, whatever, to get a tiny pump, bigger pump, all the DC pumps you want, submersible, surface pumps, anything you want. So that's really easy. Other aspects of it are more difficult, but the direct drive cookers are growing. There's a Chinese company now that makes little crock pots that are direct drive, and I understand they're selling a lot of those in the poorer parts of the world. That's great. We have one. We don't like it very much because it's low voltage, and it just shuts down with a little bit of cloudy weather. With this stuff, it's integrated with our community. I'm cooking in cold, cloudy weather.
Well, great. I think I got enough on the cookers. That was fantastic.
Okay.
And I remember the Rockwell Stan Wells used to have to build a mock-up of the Sun oven, and it gets way higher temperatures, way better insulation than the fiberglass or whatever the Sun oven has. It beats it. So.
Yeah, Rockwell's good stuff. It's a little more expensive, but it's a building material, so we don't special order it. I get it from the local building supply. Yeah. So it comes in big sheets, just like fiberglass, and it's a little more expensive, but you know, the big ticket on this is the stainless steel.
Sure.
For a cooker like this, there's probably, you know, whatever, a little over $100. Let's say $120, $130 worth of materials, and about half of that's the stainless. So yeah, and then the time to put them together. You know, when things are homemade, of course, it's all kind of slow.
Well, it looks like about 15 minutes I got left. If we can do just a quick glance at the shop, that'd be fantastic.
Sure. You know what, I mean, we can walk through the kitchen and then walk out to the shop.
Yeah. Go for it.
So with our direct drive system, it's radically cheaper, more durable than other solar systems. Once you build it, it's not free, but it's maybe 80% cheaper than a battery-based system, and you have an energy supply for the rest of your life, pretty much. So I helped friends of mine build off-grid houses, big battery bank, tens of thousands of dollars worth of batteries and inverters so they can run an AC pump so they can take a shower when they come home from work. Our solution is simply bigger water storage tanks. So that tank is about $1,000. It's not free, but it's a fiber wound tank. East Coast water is very clean, and clean water is very reactive with metal. Fiberglass tank, it lasts the rest of your life. And the other interesting thing, the whole way we have our system set up here, thermal, electric, water, the whole thing actually teaches people to conserve. So the water will drain down more quickly than the electricity. With the electricity, the difference between an AC and a DC system is an AC system runs until it stops. A DC system weakens slowly, so you get a warning. Okay, do something different or you're going to run out of power. Same with the water. It takes usually about 48 hours after somebody moves here that they realize, oh, my water usage is affected by the weather. So particularly on a cloudy day, I'm not going to water the flower bushes in front of the house at 6 p.m. I'm either going to wait until it's sunny or I'm going to do it in the middle of the day when I can run the pump. But once you get used to it, I take a hot shower year-round when I want to, more or less, because we know how to use the system. Sure. So it is not an idiot-based system, but we have hot and cold running water whenever we want it. And when we go through extended cloudy periods, we ration water use a bit. That's what we live with, but for the sake of a much cheaper energy system. So this is hot water, and this is over-the-counter technology, but I've been doing hot water for decades now, and I've learned how to do it a little better. But no new invention here, just a heat exchanger built into the tank, glycol loop up to the roof, flat plate collectors on the roof. This is the old LCID pump. LCID stopped doing business, so US Solar now makes the direct drive, just a little pump. So it's just wired into the PV panel, no thermostats, no controllers, sun comes up, pump runs, sun goes down, pump quits. That's simple, and there's a hot water supply. This will run for 30 years without me touching it. And in the wintertime, we use a little bit of wood to back it up, but not much. This is the heating blower closet for the house. So it's a conventional blower like you'd have on a furnace, except it's got an industrial DC motor on it. So when the sun's out, blower comes on, pulls the heat off the roof, blows it under the floor, keeps the house warm. We're using a few watts of electricity to capture many, many watts of thermal energy. The house, of course, is wrapped in straw bales. This is the kitchen. So we're catching thermal energy inside of a well-insulated shell. And I don't have to think about, oh, is the system overloaded? Oh, what happens if I turn this switch? I don't have to worry about that. I turn that blower on, and it runs. If the system's overloaded, it'll run a little more slowly. Doesn't matter. And in this case, so you can do refrigeration, direct drive. It is a little more expensive. We have a refrigerator we're going to look at shortly, but certainly walk-in coolers, pretty pricey if you're going to do that direct drive. You can do it. Well, air conditioners. There's a company in Virginia, there's companies in France and China making direct drive air conditioners. We don't do that. Too expensive. So we don't do, and we're largely food self-sufficient. Not entirely, of course. Canning and drying are two important methods of food preservation. So for us, we built a big closet around this heating blower, and the heat, we can blow the heat through the closet, so our heating system doubles as an industrial scale food dryer. We have stainless steel trays, so we can do fruits, vegetables, all kind of food in a dryer, and it works great. And we have, we've been doing this for years, so we've learned. Some foods work better than others. So we dry a lot of food, and we dry a lot of fruit. This whole thing about food forest, it's a little oversold. But this is about 10% maybe of our calories right here, dried as persimmons. It's a big crop in Asia. They are, you don't prune them, you don't fertilize them. We take wild persimmons, graft, mostly Rosianka and Nikita's Gift. Those are our two best ones, although we're moving into Zima Kerma and a few others. And then we dry hundreds and hundreds of pounds of these things. So we eat persimmons from August, fresh persimmons from August to February, and then February through the rest of the year we dry persimmons. I eat these at every meal. They're like jelly beans, flavor-wise, except they're actually healthy. And they're dried in there. We do a lot of dried peppers, so we grow open pollinated seeds. That's where pollen passes from one plant to another to make a seed that can then be planted generation after generation. That's opposed to hybrid GMO seeds, where the farmer has to buy new seeds from a corporation every year. So we're part of that movement to try to maintain democratic control over the food supply. And a lot of seeds, like with a pepper, we grow the pepper, we let it ripen, we pull the core out of the pepper to process for seeds. The pepper itself goes through a little slicer that's really fast, goes in the dryer, and we have lots of dried peppers as a byproduct of growing seeds. If we want to shuffle cameras around here, this is our grain mill. We do not buy any flour. We grind all our own flour. We grow our own wheat. We grow our own corn. We grow some other grains as well. And again, I don't have to think, oh my goodness, is the system overloaded? Am I going to overload my inverter? Am I going to blow a fuse? You don't have to think about any of that. You just throw the switch. You make your own peanut butter. So at Living Energy Farm, you can have a peanut butter sandwich with wheat that we grew. We ground it here. We cooked it on solar. We grow the peanuts. Shell the peanuts, cook the peanuts, grind the peanuts, right there. Peanut butter sandwich, 100% homegrown. This is another pretty significant crop for us, jujubes. Big crop in Asia. Chinese eat lots of jujubes. Most Americans have never heard of them. Just another dried fruit. Not quite as good as the persimmon, but not bad. And here's the homegrown peanut butter. So these are peanuts that we grew. We harvested them, roasted them on solar, ground them on solar, all homegrown. This is the bread, homegrown wheat, ground with solar, cooked in the solar electric oven. You're not going to do that in a sun oven in the wintertime. That's the reason I like those. This was cooked with solar energy yesterday, and it was cloudy yesterday. Let's keep going around this way. So, thermal conduction is geometrically proportional to the thermal difference. So when you got something that's really hot, you're going to get a lot more conduction than something that's not so hot. The difference between the temperature inside of a refrigerator and the outside of a refrigerator is not huge. So if you simply add some insulation, and this refrigerator is kind of dirty because we beat the devil out of it, and a dozen people use it. If you've got 5 inches of foam instead of 1 inch of foam, this has a German Seekop compressor in it. They started around 2000 making a compressor that can run 12 to 45 volts. So you can hook it to any solar panel you can find, more or less. And it gets cold and it stays cold. That's simple. Refrigerators are another huge environmental issue. I remember all the way back in the early 1980s, as a budding environmentalist, reading environmentalists who were really concerned about the growth in the number of refrigerators in China and around the world as incomes would grow. Everybody would have their own refrigerator, and it would be a terrible environmental problem. And around 2000, it was a guy named Bergeron working with NASA. I don't know if he worked for NASA or with NASA, I never was sure, who created this refrigerator, just a well-insulated DC-powered refrigerator. It gets cold, it stays cold. It's like the solar hot water, you just don't think about it. Now, it is a chest design, so you don't lose the heat, but it works really well. And they published a paper in 2000 saying, wow, we cracked the nut. We solved this huge environmental problem. Everybody can have a solar thermal storage refrigerator. It's not really more expensive than a regular refrigerator, and it eliminates this big environmental problem. Nobody buys them. Americans are so sold on the supply side approach. We're going to bulldoze the forest, which we've lost 10,000 acres within 10 miles of us, a hardwood forest being bulldozed for industrial solar fields, so people can run their leaky houses and their leaky refrigerators on what's supposed to be environmental power, and it's not. This is a better answer. And we won a competition with the IEEE, the International Electronics and Electrical Engineers Association. And there was a guy there that we met, a German fellow from who had come up with a good solution, I think, for the poorest areas of the world, where you have one good solar refrigerator, and you put it in the village store, and then people can buy blocks of ice and set up their own ice box. Because this one really wouldn't stand up to that. But he made one a little more robust. I thought that was a great idea. So you can adapt this technology even for very poor people. Certainly for middle class, so-called, people in the U.S., this is a no-brainer. And the batteries suck. You put batteries in an appliance. If you look at a refrigerator design, what comes out of China, as soon as you put a battery in it, the quality just plummets. It's the same with the whole design here. If you're tied to the grid, you're going to have crappy appliances in a poorly insulated building, because that's the design pressure. That's the shortcut. As soon as it's like pulling the needle out of your arm. As soon as you break that addiction to cheap energy, you are forced to either do without or come up with a better design. You can't have crappy design. So that's part of the reason that I really espouse this. Okay, let's do good design. Let's do it cooperatively.
And let's do what works instead of what makes some quick profit. And let's stop telling people that they can have everything they can have as long as they do it with renewable energy. That's a lie, and it's a rather vicious lie. In any case, so we do have lights at night. Who wants to sit in the dark at night? These are the nickel iron batteries. These are Changhong's. That's a company out of China. We mostly deal with ADS out of Ukraine. And yes, Ukraine is at war, but that company is still exporting batteries if you want them. You know, batteries are not a magic solution. These days they've been sold as, wow, we can do anything we want as long as we got the right kind of battery. That's not true. Batteries do not make up for bad design. And you know, I don't care. If you do direct drive, you bring the battery size down 90%, so 90% of our energy never goes through a battery. But then the battery that's left, if you want to do lithium, I don't care so much. We like the nickel irons because they're super durable. This was the technology developed by Edison back over 100 years ago. He sold lots of them. They're, in terms of watt-hour delivery, they're similar to like a good lithium, a lithium iron phosphate or lithium titanate, except they last for decades. We have a 1946 lithium nickel iron battery that works, set. This battery set is about 12 years old, still doing fine. About every 7, 8 years, you dump the electrolyte out and put some potassium hydroxide water solution back in there. It's not too hard. We do all of our low voltage stuff with cigarette lighter plugs. So the chargers that you buy to charge your phone, your laptop, your netbook, your notebook, all of that. If you're going to come stay at Living Energy Farm, you just go online and you type in whatever your gizmo name is, and you type in car charger, and you get some gizmo to plug in your car, and then you can plug it in here. The differences with our system is that, number one, it's 8 systems. It's not one. There's low voltage systems, high voltage systems. The biggest system is the 180 volt, or we usually do 90 volt direct drive. We have a battery system for the lights. There's one PV panel connected to the fridge. The hot water systems are all independent. Apart from being much cheaper and more durable, it's also fail-proof. 13 years, the lights never go out. Our neighbors would get a big thunderstorm. We had a snowstorm, knocked the lights out here, crazy snowstorm 2 years ago. And most people in this county went for power without power for 10 days. No problem for us, brush the snow off, we're good. Lights never go out. And we did take a lightning strike on this fridge 4 years ago. So it cooked a piece of electronics. Oh, so we throw bags of ice in there where we're waiting a few, it took a while to get that little thing. But it doesn't affect anything else. So we have a divided system instead of one consolidated system. It's multi-levels of voltage, it's mostly direct drive, and it's all very durable. We do some fancy electronics. This is a load diverter, so once the batteries are full, it heats up water for coffee and tea. That's just to take some of the pressure off the biogas. You want a cup of hot tea, you don't have to go burn biogas to make your hot tea. So we don't rely on little electronic widgets, but we use them some if they're convenient. So we go out to the shop?
Sure.
Are we running out of time?
We're really close.
It's 10 o'clock now.
I should probably, you've got videos with that, right? I can put links to that. Let's do it that way.
Okay.
Yeah. I appreciate this though. Whoops.
Yeah.
I hope that recovered.
Cool. Well, I'm glad you could come by.